All right. Good morning, Prince, Victor, Ray, Mitzi, Elgin, Trisha, and Rian. So, so today I think this would be the last discussion session for Math 174, and then we can all take hindi pala break ano kasi pupunta na kayo dun sa mga kailangan yung isubmit because you still owe me how many? Four things. Number one, lab exer number 6, the last laboratory exercise that would be or that is due on Monday, right before midnight. And then you still owe me the actually we owe each other yung internal evaluation. I'll give it next week. Kailangan ko lang i-finalize yung Google form, ano? So that constitutes 5 points out of 100 in your final project. And then the third one is the final project na due ay January 11. So hopefully you already have your groups with you. Siguro para mas organized pala, no? So kailangan kong malaman kung sino yung magkaka-group para pag nag-grade ako kay Canvas kasi ito na yung ano, sa susunod na panahon, ito na yung sa January, ito na yung cramming period, both for grading and computing grades. Ano. So gagawa ko ng grouping kay Canvas para isa na lamang yung mag-upload para sa group nyo. Tapos pag binigyan ko ng points yung grade submission nyo, automatically mako-compute na kay Canvas para hindi ko na siya imano-mano because there's marami nga pala kayo and yun yung medyo siguro magpapanik na ako pag i-input ng grade. So para wala akong makalimutan, we'll do a group sign up. So probably, how could we do this? We can do this in Canvas automatically. Pero, ano kaya? Or ipasend ko na lang sa inyo yung grouping. Let's see. Or kaya nyo na naman gawin sa Canvas yun. Mag-open na lang ako ng group. Pero hindi naman kayo sumusunod. So, sige, papa-email ko na lang yung name ng groups para alam ko kung sino yung group. And then the last problem set is already available. That's the fourth thing that is lacking from your final grade. So, problem set number 2 is already out. Kaka-upload ko lang kaninang umaga. Siguro nagising ako ng 4 a.m. Sinimulan ko na siyang isulat. So it's already available in Canvas. The deadline on paper is December 21st, but I will accept submissions until December 24, right before midnight. Tama ba? Or did I promise something later? Nakakahalo-halo na yung Math 191, Math 151, AMAT 255 at AMAT 350 sa utak ko. No? So, but nireview ko yung recording ng Math 174. Ay talaga, Mitzi, nangako ako ng 28. Kala ko kayo yung 24. Nireview ko yung recording, ba't di ko narinig yung 28? Pero sige na nga, sabi ni Mitzi. So, yeah, the official deadline is December 21st, but you can submit it until December 28th. I'll edit the availability in Canvas. It will be open until the 28th. You won't get any deductions if you submit it until the 28th. So, pero if you can submit early, the better because I can start grading your papers at malay nyo, mas mabait ako habang nag-check ako on Christmas Day. So, baka naman. So, i-submit nyo siya ng mas aga para hindi rin siya tumambak towards the end of the SEM. After all, 3 parts ulit yung problem set. Part 1 is an essay, so 5 questions again. Please do answer in 3 sentences or less. So, nireview ko yung questions. They are answerable in 3 sentences or less. Pag lumapas kayo ng 3 sentences, or kapag ka 3 sentences nga pero super hyper complicated, super duper long yung sentences, maminusan ko kayo ng konti. So, try to keep it short and sweet. So, meron lang mga keywords talaga na hinahanap. Except yung number 5. Your number 5, you can write a novella there, so I don't care. So yung first 4 items at most 3 sentences lamang. And if you can submit it early, again, submit it early kasi essay lang naman siya. I think that's the easiest to be done. You can do it in 1 hour or 30 minutes or less. So submit nyo na kagad pag meron na kayo. And then the second one is about numerical differentiation or numerical differentiation. I think I asked you to derive a 4-point forward formula with a personalized coefficient for f of x plus 2h as the first item. Then second, you will have to derive the total error for it. including the theoretical error and the error due to machine truncation. Tapos, kailangan yung hanapin kung ano yung optimal step size. So, yun yung tatlong steps sa problem number 2, number 2. And sa number 3, I Monte Carlo simulation naman. I gave you a two-dimensional integral, or sorry, an integral in two variables, tapos papa Monte Carlo simulation ako ng 10 beses para makakuha tayo ng isang estimate. All right? So I'll open the I'll open a meeting on the 21st. That would be on next Wednesday, but that will be purely for consultations na lamang. So papasok ako dun sa meeting, but if I don't see anyone coming in, then I'll shut it down, you know. And if na-late lang kayo ng konti and you want to meet with me next week, 8:30 to 9:30, just send me a chat kung hindi pa open yung meeting, yung online meeting, right? So ibibigay ko ulit yung link kay Canvas. So you can consult regarding the problem set and regarding the final project. Okay. But today, let's try to finish module number 11, so which is about Monte Carlo simulation. And we said this is a non-deterministic, or in other words, a probabilistic way of estimating the integral, which banks on the central limit theorem or the law of large numbers, which essentially tells us that if you do an experiment a sufficient number of times, then you will get the average return, or you'll get the expected value out of the experiment. So in terms of numerical integration techniques, the expected value that we're looking is the exact value of the integral. So the central limit theorem tells us that if you do the experiment, or if you do the simulations, taking the average of function values over the integration domain, say omega, then you will get in the long run a number very, very close to the integral itself. And we said that though this method has a very slow rate of convergence, we can compensate it by either, number one, starting with a large number of points. So because the first step here, we are selecting capital N number of points to be our simulation points, or these are the seeds in our random experiment. Ano? So palakihin mo na yung number of seeds in the beginning. More points you use, the better the approximation is. And the nice thing about Monte Carlo simulation is just function value evaluation, then taking the average, then multiply it by the size of the integration region omega, and that's it. Right? Napakasimple niyang gawin. So you can really afford to use tens of thousands, hundreds of thousands, or even millions of points. The more points, the better, especially for low dimension. But because if the dimension of the problem becomes larger, actually Monte Carlo simulation will be ideal if your integral has 6 variables or more, all right? So hindi mo na kailangan yung sobrang dami ng n. Because unlike numerical quadrature rules, the accuracy or the quality of the approximation is not dictated by, or is not hampered by the dimensionality of the problem. And it's quite the reverse. The higher the dimension, the better for Monte Carlo simulation, because it will overperform numerical integration formulas. So how is the Monte Carlo simulation being done? Well, let's take, for instance, an integral of f of x dx over an integration region omega. So here, capital X could be a function of Rn. So ibig sabihin, maraming variables yung nandun sa loob ni little f. And omega is a subset of the d-dimensional Euclidean space. So ibig sabihin, si omega ay pwedeng maging halimbawa two-dimensional. So pwedeng d equals 2. So nasa r squared ka. Region of integration mo ay r squared. So ang integral mo, dalawa yung variables. So if omega is in R3 or is a subset of R3, then we expect f to have 3 variables and so on, right? Now, the steps in the Monte Carlo simulation are as follows. First, we elect the number capital N, or we choose capital N. Usually, gusto natin si capital N ay mas malaki because we know that regardless of the dimension of the integral or the integrand, the error would be proportional to 1 over square root of n. Again, the larger of n, the better, right? But of course, that comes at a price. The higher capital N is, Though the more accurate your solution is, the more function evaluations will be needed. But again, most of the times, that's not a big deal, right? Then the second step is to draw capital N samples from omega. So meron kang integration region omega. So ang gagawin natin ay pipili na tayo ng capital N points from omega, and they will be our test points, right? So usually we choose those points to be uniform according to a uniform distribution. All right. So meaning all of the points have equal probability of being chosen as a sample point. So you can take advantage of MATLAB's RAND, then RAND of something, where this something is the size of the vector that you want. All right. So kung halimbawa, kailangan mo ng 150 seeds or 150 points, tapos na kay R2 ka, so pwede mong pagawa kay MATLAB RAND of 150, 2. So it will give you a matrix of uniformly distributed random numbers, 150 of them, na tigdadalawa yung components na laman. But be careful with this because this rand command will give you randomly distributed numbers from 0 to 1. Pero ang problema, paano kapag si omega ay hindi lamang simpleng 0 to 1? Or yung mga components ng mga elements ni omega ay hindi lang 0 to 1. So you need to search for the MATLAB documentation. Paano ko gagawin kung gusto kong random numbers ay sa pagitan halimbawa ni -1 at saka ni 1. So kailangan nyo yung i-search para dun sa problem set. Okay? Now, after you draw your sample, so kukunin natin essentially the idea kung sa one dimension, kukunin mo yung area ng mga rectangles wherein the length of omega. So kung nasa one dimension tayo, so d is equal to 1, so omega is just an interval. So yung Monte Carlo simulation, kukunin niya yung area ng mga rectangles that are dependent on the random seeds that you have chosen. Yung length ng mga rectangles would be the length of omega. Then the heights of the rectangles will be the function values at the chosen seeds, right? So magiging b minus a times f of x sub I, right? So here, b minus a is the length of omega, which we usually denote by the absolute value of omega. Yun yung size ng integration region. So size ng integration region times function value nung doon sa ating randomly chosen points, there would be capital N of them, then take the average, then that's going to be your estimate for the integral. Kung two-dimensional naman si omega, ibig sabihin si omega halimbawa ay isang rectangle, okay, over the two-dimensional space, ano? So kung rectangle si omega, tapos meron kang function value, so halimbawa ito yung seed mong napili, kukunin mo yung function value niya, f of x sub I, tapos ang kukunin mong measurement sa kanya ay yung volume. Hindi ako magaling mag-drawing ng 3D or mag-drawing ng kahit ano, pero ang kukunin mo ay yung volume nung rectangular prism formed by omega as your bed, and then the height of that rectangular prism would be the function value at the chosen seed x sub I, where x sub I is a point in the two-dimensional space. Kukunin mo yung mga volume, kukunin mo yung mga average ng mga volumes na yon, then that's gonna be your estimate for the integral. So in general, that will happen. So the formula that we're using is 11.1. So you get the function value times v, which is the volume of omega, right? When omega is just one-dimensional, then v is just the length of omega. If if omega is two-dimensional, then v is just the area of omega. Tapos pagka three-dimensional and so on, volume pa rin yung tawag natin doon. So we're just taking the average size of the d plus 1 dimensional surface that is bounded by omega as a bed, and the function value as the height. So yun yung binibigay sa atin ng 11.1. And I think we experimented last time with a one-dimensional function, which is this highly oscillatory function x sine x cubed. And the graph is this, and you will right away see why numerical quadrature formulas, especially done when you have a small number of points, in the quadrature formula, will fail, because if your mesh points, or if your quadrature points or abscissas are to be chosen sparsely over the integration interval, then makikita nyo na hindi nyo makakapture yung oscillatory behavior nung function, right? Kaya naman they are doomed to fail, especially those that only use, say, trapezoidal rule na dalawa lang, or Simpson's rule na 3 points lang, and so on. Okay, kaya kailangan talaga either marami kang points na gamitin or mag Monte Carlo simulation ka na lamang. And there are several variants of the Monte Carlo simulation. Number one is the simple Monte Carlo simulation, which is illustrated in problem number 1 in the module, wherein we used 100 points. Pumili lang ako ng 100 random points over the integration interval 0 to 4, and then used formula 11.1 para sa kanila. And here's the result. So ito yung 100 sample points or plots ng 100 sample points. Then ang ginagawa ko dyan, halimbawa sa sample point na to, kukunin ko yung area ng rectangle na to. Computing ko yung area ng rectangle na yan, and I will do this for all of the random seeds, right? Tapos kukunin ko yung average ng 100 areas ng rectangles na yon. Yun na yung estimate ko para dun sa integral from 0 to 4. And I think here we didn't get too much good a result, kasi nga 284% yung error. Which is understandable because we only used 100 points. Remember, the error is root of 100. So that's 1 over 10. But this is just approximative. Hindi siya error bound. It is just an approximative value for the error. So we were expecting around 0.10 na error. Okay. Pero ano ba yung actual integral? The actual integral, I think, is what? What's the actual value of the integral? The value of the actual integral is 0.35. So that's 0.10 divided by 0.35. So that's going to be about 10 over 35. So about what? 1 over 3.5. So about 3%. So ito yung a priori estimate natin. Around 3% supposedly yung error. Pero dito 284% yung error. That reminds me to tell you that this 1 over square root of 2 error here is a proportional estimate, or an estimate for the constant of proportionality. It's not an error bound. Hindi siya katulad ng mga na-establish natin na theorems dati na sure tayo na yung mga errors ay hindi lumalampas doon sa halimbawa n plus first derivative ni f evaluated at psi all over n plus 1 factorial times the norm of omega. So hindi siya ganun. Kasi dito ito ay parang estimate lang galing sa what do you call this? Galing sa central limit theorem. Ang sinasabi niya is, as capital N goes large, right, yung error ay palapit ng palapit kay 1 over root N. Hindi siya upper bound. Siya yung long-term behavior for sufficiently large value of N. And apparently, 100 is not good enough. Right? So what we can do if our case is like that, we first try to increase the number of points. Yun yung ginawa sa bullet number 2 here, dahil kulang yung 100 sample points. Gumamit tayo halimbawa ng 25,000 random seeds over 0.4. Okay? Tapos tingnan natin yung resulta. Okay, let's see. Yeah. Using 25,000 points, I got 0.4196 as my estimate. And that's now a little better. It's at 17%. I said a little better kahit ang laki ng improvement from 284% to 17.68%. Hindi pa rin siya ganun kaganda kasi more than 10% pa rin yung error. Again, this is 1 over 2,500. Pag kinuha natin yung square root niyan, wala to, 250, 50, 1 over 50. Ay, hindi pala, no? So, yeah, it will be that number. hindi pa rin siya ganun kaganda, yung 25,000 points, right? So if you cannot afford to increase the number of draws or the number of random seeds that you're using, you can run Monte Carlo simulations multiple number of times using the maximum number of the maximum value of capital N that you can, and then take the average of those runs. Ito yung parang multiple Monte Carlo simulation runs. Hindi na siya yung simple. Kasi ngayon sa number 3, ang ginawa ko, nag-stick ako sa 25,000 points, pero ginawa ko yung simulation multiple number of times. Right? So, ibig sabihin, every time pumipili ako ng 25,000 sample points. And this is usually the case, right? So, we do not just increase the number of points kasi redrawing uli yun, redrawing, and so on. And usually, there's a limit to the capital N that we can use, lalo na kung super komplikado si F, tapos medyo mabagal yung computer natin, hindi tayo pwedeng gumamit ng 100 million points. Ano? So instead of that, we perform Monte Carlo simulations multiple times. So that's what was done in number 3, wherein I still used 25,000 sample points, pero inulit ko ng 5 beses yung Monte Carlo simulation. So in our first set of draws, nag-draw tayo ng 25,000 sample points. Nakuha ko si I1, yung 17.68% na relative error. Tapos, ginawa ko, okay, hindi ako kontento dyan, right? So, ang ginawa ko, next round, inulit ko yung Monte Carlo simulation, but when I repeat the Monte Carlo simulation, I am generating another bunch of random numbers. So I drew another 25,000 sample points, and then take the average of omega times the function value at those 25,000 points, and I get this pretty good estimate, 5%, right? Kung alam ko kung ano yung ine-estimate ko, then this is perfect because I can just report I2 as my best answer. Kasi alam ko na ito, 5% lang yung error. Pero in reality, we don't have information about what's the true value, alright? Ginawa lang natin to kasi binavalidate natin yung method. Pero sa totoong buhay, wala kayong access dito. You don't know what the exact value is, so it's very difficult to get an estimate for the relative error. So, kaya ang ginawa ko, okay, third round, mag-Monte Carlo uli ako, 25,000 sample points uli. I got this number, right? We know that that's 6% accurate, which is very good, ano? And then do it fourth time, fifth time, and to get the best approximate. If we don't have any idea about the relative errors, ano, so kukunin ko ang i-report ko na estimate from the Monte Carlo simulation will be the average nitong 5 na ito. Of course, kung alam mo yung relative error, edi ang i-report mo si I5 kasi less than 1% yung error dyan. Pero dahil kunwari wala tayong idea about sa relative error, kunin mo yung average ng mga results dun sa 5 Monte Carlo simulations, and then you'll be good. Right? Ito yung usual na ginagawa sa Monte Carlo simulations. You choose capital N, but you perform Monte Carlo simulations multiple times using N sample points, and then you take the average of the results of each of the runs para makakuha ng isang magandang estimate. Okay. Now, so that's one trick, but there's also what we call an adaptive Monte Carlo simulation, wherein we can take advantage of our knowledge of what the integrand is and how it looks like, right? So, halimbawa, alam ko na yung integrand ay napaka-wiggly or napaka-oscillatory like this. So, I can decide to smartly allocate the drawing of the points over the interval kung saan mas nagiging messy yung itsura ng function. For instance, in bullet number 4 here, sinabi sa atin na, okay, i-divide natin yung buong interval into 2 subintervals. Yung unang subinterval, posibleng dito muna yung hindi pa masyadong makulit. So to speak yung function, hindi pa siya magalaw, hindi pa siya masyadong nag-oscillate. Tapos yung second interval, A2 to B2, doon naman siya napaka-oscillatory. And we can allot more points doon sa second interval. Kasi alam natin dun sa second interval, mas crazy yung behavior ng function. So we will adapt our randomization. Mas maraming random points dun sa mas problematic na interval. And that is hinged upon the linearity property of the integral. Na yung integral, pwede nating i-split into two integrals, and then we perform Monte Carlo simulations on the two intervals with different values of capital N. Okay, halimbawa, dito sa number 4 na to, ang unang suggestion ay 100 points pa rin yung gamitin, pero 10 lang yung gamitin natin sa interval 0 to 2, tas the remaining 90% will be allocated on the interval 2 to 4. Bakit? Kasi from 0 to 2, ito yung graph natin, or ito yung function natin dyan, hindi pa siya ganun kakulit. Ano? Hindi pa ganun kalikot yung function. Pero sa 2 to 4, makikita nyo na, ayan na, gumigiling na siya, no? Nag-oscillate na siya doon sa interval na yon. So we will allot 90 points, or we'll force our randomization to produce 90 points on the interval 2 to 4. And true enough, this is the results I got. 0.52, which is 46%, which is 6 times better than, or around 6 times better than what we got originally. Same 100 number points, pero 46% yung error. Although I could have just been lucky with number 4 when I drew the 10 plus 90 sample points, or I would have been very unlucky when I drew the 100 points in number 1. Pero number 4 makes sense. Ano? Yung stratification na ginawa sa number 4 really makes sense. So hindi lang ako umaasa sa swerte. Kasi yung number 4, it comes with an intelligent allocation of the seeds for the Monte Carlo simulation. So hindi talaga yung mga, kahit may Monte Carlo simulation ka na, hindi sila kailangang maging black boxes na mag-input ka lang ng function and then you will rely on your luck. Mga mathematicians tayo, umiisip tayo ng paraan kung paano mas effectively mapagana yung mga algorithms. Ano? Lalo na sa Monte Carlo na it's a hit or miss. We want to increase our chances of hitting the number that we are approximating, right? So, yeah, ito yung itsura ng 90 plus 10 plus 90 na discrete na randomization. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the 10 points na inallocate natin sa 0 to 2, and then the overwhelming majority of the points were allotted from 2 to 4. And hence we get a better sampling of the oscillatory behavior of the function little f. Compare niyo yan dun sa figure 11.5 na kakaunti lamang yung points na nandun sa parte kung saan mas magulo yung behavior ng function. Alright? Okay, so that's one way to do it. Tingnan ko yung number 5. Anong ginawa sa number 5? Dun sa number 5, mas heavy na stratification. So in number 5, we will repeat the experiment in number 4, except na 25,000 points na yung gagamitin natin, 100 of which would be on 0 to 2, and the remaining 24,900 ay nasa 2 to 4. Okay. So ito yung stratification na naganap. Alright. So it's as if kita nyo, napaka-dense nung randomization dito or yung drawing dito sa 2 to 4 kasi nga 24,900 random points yung pinili ko. Dito 100 lang. Pero it seems that 100 would be enough because my function over the interval 0 to 2 is not that wiggly. Ano? Hindi siya masyadong magulo or malikot. And true enough, in number 5, I got an estimate of around 0.37, which has relative error of just around 4.91%. Compare nga natin to dun sa kanina, dun sa full 25,000. Dun sa full 25,000 na first draw, 17% yung nakuha ko, right? Pero nung nag-stratify na ako, I got 4.91%. So I did a smart choosing of the random points. Ano? Meanwhile, pinakamaganda pa rin yung 5 beses tayo nag 25,000 points. kasi 1.58% yung error na binigay sa atin. But of course, everything here is random. So, ibig sabihin, it is not a fair comparison. Malay nyo, sinwerte lang ako dun sa ilang mga draws dito. And another thing is that if you'll try to recreate this in MATLAB or in any programming software, ay posibleng hindi nyo talaga makukuha yung eksakto or almost impossible na makuha nyo itong mga eksaktong numbers na nasa module. Kasi random nga eh. So, iba-iba yung bunot natin ng 100 o ng 25,000 points over the integration interval. Okay? So I think that covers example 11.1. Do you guys have any questions about it before we jump to the two-dimensional example? Wala pa naman? Mukhang simple pa lang siya, no? Pero malamang iniisip nyo na rin na ay kapag ka nagpa-exer na saka po kami magkakaroon ng questions or nagpa-problem set na. That's why I hope you find time probably. I don't know if you can still insert it. Try to look at the problem set the next few days. Tapos sa Wednesday, pwede nyo akong tanungin. Kung medyo may mga mahirap na parts, hingan nyo ako ng hint sa Wednesday. Kaya i-open ko pa rin yung Teams meeting natin on Wednesday so you can ask for hints or clarificatory questions about the problem set and the project. I'll be happy to guide you. All right? Pero hindi ko siya i-record. So, kailangan yung magtanong at pumunta dun sa mismong session. Okay. So, let's try a two-dimensional example. That's example 11.2. So, we are doing an integral over r squared over a subset of r squared omega. So, dito mag-i-integrate tayo ng y sine x minus x cosine y over the rectangle negative 4 to 5 and negative 5 to 4. Sana tama na to. Let's see. Naalala ko last year na pagbaligtad ko yung integration bounds. Hopefully na-edit ko na itong module na to. But yeah, let me see if you're trying to recreate it and you're not getting the same answers. Because I might have flipped the bounds. I need to double check this. Kasi dy dx. Tanda ko parang last year, nung first version ng module, dx, dy yung na-integrate ko. Pero dapat dy over dx, and that's crucial because I don't have a symmetric bounds for integration. So magkaiba yung bounds for y at saka yung bounds for x. But nevertheless, our integration region omega, so kung kukunin natin yung omega natin on two dimensions, right? So y goes from negative 4 to 5, and then x goes from negative 5 to 4. So ito yung ating integration region omega. Right? Tapos pipili tayo ng isang point dyan sa omega na yan. Right? So pili ako halimbawa, ito yung aking point na napili sa omega na yan. Kukunin ko yung function value ng random point na yon. Right? Meron siyang x at saka y component. Then siya yung magsaserve as height dun sa rectangular prism na kukunan ko ng volume, tapos gagawin ko yan sa lahat ng random points, i-average ko yung mga volume ng mga rectangular prisms na yon, and that's what I'll report as my estimate for the integral. All right? So yeah, this is the exact value if you'll do multiple integrations. So you're going to get negative 3.5. Pero magmo-Monte Carlo simulations tayo rito. Okay. But first, let's take note of the size of omega. Now, omega is the rectangle negative 5 to 4 cross negative 4 to 5. So, ang V, which is the volume of omega, or if you want to be localized here, the area of omega is 81 units, right? Kasi yung x components niya, negative 4 to negative 5 to 4, so that's 9 units. This is also 9 units. So omega is actually a square, right? Of side length equal to 9. So dahil isa siyang square na ang side length ay 9, so ang volume niya ay 81, o ang area niya ay 81. So we will have 81 over n times the summation of mga function values over x and y's chosen randomly over omega. Okay. Unang instruction, gumamit tayo ng 100 points. Ipa-plot ko yung sample points on top of the graph of f. So ito yung makukuha ko dyan. So ito yung surface para kay f, right? So you need also to search MATLAB paano ba nag-graph ng three-dimensional figure, all right? So hanapin niyo sa help ni MATLAB. Maganda naman yung documentation ni MATLAB, so search for it. And then pinlot ko on top of it yung scatter plot ng mga random points. So at yung mga blue dots dyan, yan yung mga sample points na pinili ko. And here's a two-dimensional look at it. So this is the region omega. Okay. -5 to 4 lang yan. So hanggang dito lang yan. Oops, sorry. -5 to 4. Tapos -4 to 5. So ito lang yung rectangle natin ginagalawan. Right. So dyan sa grid na yan, -5 to 4 and -4 to 5, ako pumili ng 100 random points. Sila yung mga dots dyan. Alright? Tapos ang idea ay, so meron akong rectangle dito. So ang y ko ay -5 hanggang 4. Tapos meron ako ditong ganun din, -5 to 4. Tapos meron ako nito. So ito yung projection ni omega. Right. Tapos, halimbawa, ito yung random point na napili ko. Yan yung magsiserve na height. Right? So I'm gonna have, okay, have this. Oops. Tapos ito. Meron na akong guide, nagano pa rin siya. Naging slanted pa rin. Pero imagine, it's a nice rectangular prism. Ano? So it's a rectangular prism with base area 81. Tapos yung height niya ay f of the chosen point, the chosen random point. Tapos ito yung volume niya. Kasi average ko lang yung 100 volumes na yan, yan yung i-report ko as the value of the integral. And if you do that, ano yung nakuha ko? I got 7.83, which is, or with relative error, 300%. So again, 100 points is not enough. So ang ginawa ko sa number 2 naman, gumamit ako ng ilan? 100,000 random points para dun sa Monte Carlo simulation. So, ito yung 5 sample na tig 100,000 points yung ginamit. So, I had results as good as what? 2% relative error. 100,000 points na to pero meron pa rin akong results ng error ay umabot ng 19%. So that's a very big range, no? From 2% error to 19% error. At ang laki na to, 100,000 points. This is 1,000 times more or denser than number 1. Pero okay na rin kasi from 300% bumaba na siya sa at worst 19.38%. Right? So yan yung 5 draws na tiga 100,000. And again, to get a better estimate, average the results of your Monte Carlo simulation. Pag in-average ko yan, I'll get 4.59% error, and that might be enough for some applications. Pero pinush ko kasi yung computer ko niyan kung hanggang saan yung kaya niya. Ano? So ang ginawa ko, medyo naglaro pa ako ng konti. So gumamit ako ng 10 milyong sample points. Tapos inulit ko siya ng ilang beses. Tapos in-average ko siya. Alright? So ito yung mga naging result ko. So 10 million at 2.04% error yung nakuha ko. And you see that 2.04% error is still a little worse than, slightly better lamang with the first simulation I got with 100,000 points. Ano? So ganun ka hit or miss ito, lalo na sa lower dimensions. Na kaya kong kumuha ng 2% error kapag ka 100,000 points lang yon. Pero medyo minalas ako dun sa unang draw ko using 10 million points. Nasa 2% pa lang din yung error. Pero running it several more times, I got about 0.50% error hanggang 2.89% error. Pero parang hindi na siya lumampas ng 5%, ano? Unlike dito na umaabot pa siya ng 20%. Kasi nga masyado ng marami yung 10 million points, it's good enough for most Monte Carlo simulations. But again, that very slow convergence pa rin is attributed to the fact that we are only in the second dimension, or 2 lang yung dimension ng integral natin. So we expect Monte Carlo simulation to be spectacularly slow, right? And I guess that's it. So tapos na tayo ng Math 174. Yay! Ito yata yung binigay, hindi. Binago ko tong, ginawa kong 1 to 2. Ito yung binigay ko dun sa problem set, ano? But okay, I think that's it. So do you have some questions about this? Siyempre wala pa kasi wala pa yung hindi niyo pa nakikita yung problem set, ano? But any other concerns? So if there are no more questions, then I think that's it. I had a fun semester. Hopefully you did too. I hope you learned something aside from mahirap pala yung laboratory exercises, ano. But I hope you also pick something from the lab exercises kasi they are designed not just to test your understanding but also to teach you some things. At ginagamit ko rin siyang springboard para dun sa susunod natin na topic. So yeah, though we're done with the discussions, I hope to see you around. If you have some questions, kahit saan yan, ACAD-wise, or gusto nyo lang ng kachismisan, just let me know. Hit me up with an email. And but as far as 174 is concerned, you still owe me the internal evaluation, which will be out next week. That's 5 points out of the 100 for your final project. Lab Exercise 6 due on Monday. Problem set number 2, which is officially due on the 21st, but you can submit until the 28th. And then the final project, which will be due on January 11. And then I'll ask you guys to fill out a Google form para dun sa grouping, ano? So at least magpadala kayo ng isang member na ano na lang sa sign up sheet, ano? Para nagawa na ako ng sign up sheet, ano? So paki-identify na lang doon yung groupings nyo. Tapos doon ko kokopyahin para ma-assign ko kay Canvas kung sino yung magkaka-group. Para isa na lang yung mag-upload, tapos automatically makikita ko na lahat meron nung submission na yon kay Canvas. Okay? So yeah, any other concerns or questions? So kung wala na, probably for the last time, thank you guys for joining me today. Have a happy weekend. Have a happy holidays, ano? And I'll see you around, guys. Bye-bye.
Thank you, sir. Thank you, sir.
All right.